Right now, as you sit here listening to this, our entire galaxy is moving, not just spinning on its axis, not just orbiting the sun, not just drifting through the Milky Way. The Milky Way itself, hundreds of billions of stars, planets, nebulae, black holes, is being pulled toward something. An invisible gravitational monster hiding in the darkness. We can't see it directly. It's buried behind the thick dust of our own galaxy. And yet, everything in our cosmic neighborhood, including you, is rushing toward it at hundreds of kilometers per second. Astronomers call it the Great Attractor. At first, it sounded like science fiction. A mysterious force, a hidden mass concentration, tugging on entire clusters of galaxies. It shouldn't be there. Not like this. Not with this strength. And here's the problem. The more we've tried to understand it, the stranger the picture becomes. Our galaxy isn't just falling toward a single point. It's part of a vast cosmic current, a river of galaxies, streaming through a landscape of invisible structures, voids, and titanic clusters. If we're right about what's out there, our entire idea of where we live in the universe, and where we're going, may change forever. What if everything we thought we knew about our galaxy's place in the cosmos is wrong? Tonight we follow the evidence. From the first hints that something was pulling on us, to modern maps of the cosmic web that reveal a universe far stranger and far more dynamic than we ever imagined. Today, we journey through evidence that challenges everything. Prepare yourselves. We begin. The discovery. We've always known we're in motion. Earth spins once every 24 hours. We orbit the sun once every year. The sun orbits the center of the Milky Way every 230 million years or so. But in the 20th century, astronomers discovered another motion. A deeper one. A motion not around anything inside our galaxy, but a motion of the galaxy itself. When astronomers measured the faint glow left over from the Big Bang, the cosmic microwave background, the CMB, they expected it to look almost perfectly even in every direction. Instead, they saw a tiny temperature difference. One side of the sky was slightly hotter, the other slightly colder. This pattern, called the CMB dipole, was the giveaway. It meant that we were moving relative to this ancient light. Like sticking your hand out of a car window and feeling the air. One side hits harder. When astronomers calculated that motion, they got a huge number. Our local group of galaxies, including the Milky Way, is moving at roughly 600 kilometers per second relative to the universe's rest frame. 600 kilometers every second. Faster than anything we can build. Faster than we can truly feel. The question was obvious. What is pulling us? The Seven Samurai. In the late 1970s and early 1980s, a group of astronomers set out to answer that question. They would later be nicknamed the Seven Samurai. Alan Dressler, Sandra Faber, Donald Lindenbell, Roger Davies, Roberto Turlevich, Gary Wegner, and Gustav Burstein. They used a clever trick. Normally, galaxies appear to be rushing away from us because space itself is expanding, the famous Hubble expansion. The farther a galaxy is, the faster it should be receding and its light is stretched or redshifted. But what if a galaxy is also falling toward some nearby mass? Then its motion won't match the simple Hubble law. This extra motion, the motion on top of the cosmic expansion, is called peculiar velocity. If you can measure a galaxy's true distance one way and its redshift another way, you can separate the smooth expansion from these peculiar velocities. That tells you how gravity is tugging on that galaxy. The Seven Samurai collected distances and redshifts for hundreds of galaxies. Then they mapped how those galaxies were drifting relative to the expanding universe. They expected something messy. Instead, they saw a pattern. Many galaxies in our region of the universe were flowing in the same general direction, toward the constellation of Centaurus. It was as if all of them, including the Milky Way, were sliding down the same invisible slope. Dressler gave it a name. The mysterious mass pulling on us became known as the Great Attractor, a hidden monster. There was a problem. When astronomers pointed their telescopes toward the region of the Great Attractor, they didn't see a gigantic obvious object. The direction of the pull lies in a part of the sky clogged with stars, dust, and gas from our own galaxy, an area called the zone of avoidance, because it makes deep surveys extremely difficult. Behind that curtain, the data hinted at something big, an enormous overdensity of galaxies and dark matter, but not a single neat object, like a single monster cluster. Some galaxies showed peculiar velocities of up to several hundred kilometers per second, either toward or away from this direction, depending on which side they were on. Nearby galaxies had peculiar velocities in the range of roughly plus 700 to minus 700 km/s relative flow. Something very massive, very extended, was there. But here's where it got strange. As more data came in, it became clear that the Great Attractor might not be the final explanation for our motion. The flow didn't stop at the Great Attractor. It seemed to continue past it. The evidence was forcing astronomers to confront an uncomfortable possibility. The Great Attractor might just be one part of a far larger and more complex gravitational landscape. Later, dramatic. But the evidence forces us to confront an uncomfortable possibility. We are not falling toward a point in space. We are being carried by a river of gravity. Through a hidden cosmic landscape we have only just begun to map.
Act 2. Accumulating evidence. Part A. Observable signatures. To understand the Great Attractor, astronomers started mapping the universe in 3 dimensions. They used large redshift surveys, like the IRIS survey and later the Sloan Digital Sky Survey, to chart tens of thousands of galaxies. Each galaxy's position and redshift became a point in a vast cosmic map. On these maps, structure emerged: long filaments of galaxies, dense clusters, and huge, nearly empty voids. In the region of the Great Attractor, they found not a single, isolated beast, but a complex of clusters and filaments. One of the central players is the Hydra-Centaurus supercluster, a massive concentration of galaxies about 150 to 200 million light-years away. Nearby lie other giants: the Norma cluster, the Pavo-Indus telescopium complex, and additional clusters revealed by X-ray surveys that could see through the dust of our galaxy, like the CZA catalog, which used X-ray instruments to uncover hidden clusters in the zone of avoidance. OUP Academic. Each of these is like a mountain in a gravitational landscape. Each adds its pull to the overall stream. Evidence number 1. Peculiar velocities. Galaxies in our region show coherent bulk flow, a large-scale motion of about 600 kilometers per second toward the Great Attractor's rough location in Centaurus, derived from distances and velocities of spiral galaxies and clusters. Evidence number 2. CMB dipole. The temperature pattern in the cosmic microwave background aligns closely with this flow. The direction of the CMB dipole, the hot side of the sky, points toward almost the same region, confirming that our entire local group is moving that way relative to the early universe. Evidence number 3. Redshift space distortions. In redshift surveys, galaxy clusters near the Great Attractor region appear squashed or stretched along our line of sight, a telltale sign of gravitational infall. Galaxies falling toward a mass concentration distort the pattern of redshifts, revealing the presence of a massive overdensity. Together, these clues told a consistent story. Something in that direction was massive enough to bend the paths of thousands of galaxies. But how massive? Estimates suggested that the Great Attractor region might contain the equivalent of tens of thousands of Milky Way, like galaxies in mass, when you include not just the visible galaxies but the surrounding dark matter halo. Even so, when astronomers tried to account for all the mass they could see in Hydra, Centaurus, and neighboring clusters, the numbers didn't quite add up to the full motion we observe. There was still a missing piece. Narrator. This was just one piece of a much larger puzzle. 25:00, 35:00, Part B. Deeper implications. Music grows more intense. Visuals. Zoom out from Great Attractor to show larger cosmic environment. As surveys grew deeper, astronomers looked beyond the Great Attractor. What they found suggested that our motion might be influenced by even larger structures. Behind the Great Attractor region lies a truly titanic mass concentration: the Shapley supercluster. The Shapley supercluster contains dozens of rich clusters and thousands of galaxies, and is one of the densest, most massive structures in the nearby universe, about 500 million light-years away. Some studies suggest it could account for roughly half of the mysterious motion once attributed solely to the Great Attractor. The idea is unsettling. We are not just falling into one valley. We may be sliding downhill toward an even larger basin of attraction, with the Great Attractor as merely a foreground slope. Then, in 2014, a team led by our Brent Tully unveiled something extraordinary. They used galaxy distances and velocities from the Cosmic Flows project to trace how galaxies are actually moving through space, like watching the currents in a cosmic ocean. When they followed these streamlines of motion, they found that our local group, the Great Attractor region, and several neighboring structures all belong to a much larger gravitational basin. They called this basin our home supercluster, Laniakea, Hawaiian for immense heaven. Laniakea stretches about 500 million light-years across, containing perhaps 100,000 galaxies. It's not defined by where galaxies are, but by how they move. Everything within Laniakea flows inward toward a central region, a basin of attraction. And that basin? Its location coincides with what we once simply called the Great Attractor. Evidence number 4. Flow lines. Cosmic Flows reconstructions show galaxies within our region streaming toward a central attractor located in the direction of Centaurus, consistent with the classic Great Attractor direction, but now embedded in a vast Laniakea basin. Evidence number 5. Volume of the basin. The segmented Laniakea basin occupies a volume of around 2 million cubic megaparsecs, confirming that the gravitational influence responsible for our motion extends across an enormous swath of the local universe. Evidence number 6. Multi-scale flows. Our local group's peculiar velocity can be decomposed, partly from the pull of the nearby Virgo cluster, partly from evacuation from the local void, and significantly from large-scale flows toward the Great Attractor and beyond toward Shapley, showing that our motion is the sum of multiple gravitational tugs across different scales. In other words, the Great Attractor is not a single object. It's the central gravitational node of our home supercluster, a region of space where the entire cosmic landscape slopes inward. But that realization creates a deeper question. If our supercluster flows toward the Great Attractor, and the Great Attractor itself flows toward Shapley, are we part of an even larger, hierarchical cascade of motion? Narrator low. The evidence extends beyond a single attractor, into the realm of a cosmic river, flowing through an immense web of structures.
Act 3. The Big Picture. Part A. Theoretical Framework. To understand what the Great Attractor really is, we need to zoom out, not just in space, but in time. Shortly after the Big Bang, the universe was almost perfectly uniform. Tiny fluctuations in density, parts slightly heavier, parts slightly lighter, were imprinted in the hot plasma and later in the cosmic microwave background. Over billions of years, gravity amplified these tiny ripples. Regions with slightly more matter pulled in more and more material, growing into galaxies, clusters, and superclusters. Regions with less matter became voids, enormous cosmic bubbles with very few galaxies inside. This process is known as gravitational instability. Under it, the universe naturally forms a cosmic web, filaments of dark matter, and galaxies connected at massive nodes, with voids in between. In this picture, the Great Attractor is not a mystical anomaly. It's a node in that web, a region where density is higher than average, creating a gravitational basin. The motion we observe, our 600 kilometers per second drift, the peculiar velocities of neighboring galaxies, are the result of matter cascading down the slopes of this basin. Modern cosmology models this using the lambda CDM framework, a universe filled with dark energy lambda, cold dark matter CDM, and ordinary matter. Simulations of structure formation in lambda CDM naturally produce large structures like Laniakea and Shapley. But there are still big questions. How exactly is mass distributed in and around the Great Attractor? How much of the flow is due to Shapley versus more nearby structures? Are there even larger basins of attraction beyond our current horizon of surveys? Various research teams have proposed different models of a local velocity field, treating the Great Attractor and Shapley as overlapping or connected basins. Some reconstructions suggest that Laniakea, Shapley, and neighboring superclusters may themselves be part of an even larger Pisces, Cetus superstructure. In simple terms, we may live not just in a supercluster, but in a multi-level hierarchy of gravitational basins that forces us to reconsider some of our fundamental assumptions. We often teach that on large scales, the universe is homogeneous and isotropic, the same in every direction. But structures like the Great Attractor and Shapley are not small. They stretch across hundreds of millions of light years. The universe might look smooth if you zoom out far enough, but locally, it is intensely structured. Narrator. This forces us to reconsider fundamental assumptions about our cosmic neighborhood and reminds us that average does not mean featureless. Part B. Future implications. So where does this leave us? We've identified the Great Attractor region. We've mapped Laniakea as its larger basin. We've connected it to Shapley and beyond. But we're not done. Ongoing and future surveys are sharpening this picture. Cosmic flows, for and beyond, expanding catalogs of galaxy distances and peculiar velocities, giving us ever more detailed flow maps of local cosmic motions. Deep redshift surveys from facilities like the Anglo-Australian Telescope, ESO's VLT, and others continue to uncover new clusters in the zone of avoidance, reducing blind spots in the Great Attractor region. Wide field surveys like DESI and imaging from Euclid and the Vera C. Rubin Observatory will map the large-scale distribution of galaxies and dark matter with unprecedented precision, revealing the full extent of superclusters and voids that shape our motion. Scientists are also using numerical simulations to ask, given the observed distribution of mass, should we expect a motion like ours? Do our models naturally reproduce a flow of 600 km/s in this direction? Or is there tension? If future reconstructions find that our motion is larger than expected, or points toward structures more massive than lambda CDM comfortably allows, it could hint at new physics, modifications to gravity on large scales, or unexpected behavior in dark matter or dark energy. At the same time, these studies tie into a broader question. How typical are we? Is every galaxy in the universe part of some giant flow toward a nearby attractor? Or are we in a particularly dynamic neighborhood, near an especially dense region of the cosmic web? Recent breakthroughs suggest that our local environment, including the local void, the Virgo cluster, and the Great Attractor basin, is complex and somewhat special. Our peculiar velocity is not zero. We are not just drifting passively with the expansion. We are surfers on a gravitational wave, being steered by the uneven distribution of matter around us. For humanity, this has profound implications. It means our address in the universe is not just a set of coordinates. It's a trajectory. We are not stationary observers watching the cosmos evolve around us. We are passengers on a moving platform, being carried through the universe by forces stretching across hundreds of millions of light years. And that raises a deeper question still. If we are being pulled somewhere, where are we going? Act 4. The Ultimate Questions. This is where the implications of the Great Attractor become truly mind-bending. We often imagine the universe as a static backdrop, an enormous stage on which galaxies slowly drift apart. But the reality revealed by the Great Attractor is more like a cosmic river system. Voids act like high ground where matter drains away. Filaments are rivers of galaxies. Superclusters are confluences, great basins where these rivers merge. We live deep inside one of these drainage systems. Our galaxy is a tiny boat in a gravitational current flowing toward the bottom of a vast cosmic basin. Now, consider this. If gravity keeps pulling, and if dark energy keeps accelerating the expansion of the universe, there will come a time, trillions of years from now, when distant structures slip beyond our cosmic horizon. Only the galaxies gravitationally bound to us will remain visible. Which structures we end up bound to depends on the very flows we're mapping today. The Great Attractor and Laniakea may help determine the ultimate island of matter that future civilizations will see when the rest of the universe fades from view. In a sense, the Great Attractor is part of our cosmic destiny. But the philosophical implications go deeper. Implication 1. We are not at rest. There is no privileged, still vantage point in the universe. Even our rest frame, defined by the cosmic microwave background, is just another frame, and we are moving through it. The Great Attractor reminds us that everything is in motion, on every scale. Implication 2. Our environment shapes what we can observe. The fact that we live near a void on one side, a cluster on another, and a basin of attraction in a particular direction, changes the pattern of galaxies we see in the sky, the dipole in the CMB, even the gravitational lensing we can measure. Our local cosmic geography is not just a curiosity. It's a filter on our view of the universe. Implication 3. Cosmic principle under scrutiny. On very large scales, the universe may be homogeneous. But locally, the presence of huge attractors, voids, and flows raises questions about how quickly that homogeneity is reached. Are we in a region that's statistically typical? Or are we in a somewhat unusual neighborhood of the cosmos? Implication 4. Hidden structures beyond our maps. If Laniakea and Shapley are part of a larger superstructure, then beyond the edges of our surveys may lie even more massive attractors, shaping motions we haven't fully accounted for. Some reconstructions already hint that Laniakea may merge into even larger complexes, suggesting our current maps are just the beginning. And finally, implication 5. Our story is part of a bigger flow. Every human story, every civilization, every moment of history, from the first sparks of life on Earth to the launch of the first telescope, has unfolded inside a galaxy tumbling through space along a path we did not choose and barely understood. Our myths placed us at the center of everything. Then we learned we orbit the sun. Then that the sun orbits the galaxy. Now we know the galaxy itself is being carried by forces spanning hundreds of millions of light years. Each step pulls us further from the illusion of cosmic centrality and deeper into the wonder of a universe too vast to fully grasp. The most profound implications emerge when we consider this. We are not outside the story of the universe, looking in. We are inside the current, stardust, atoms, and consciousness, carried by a river of gravity toward an unseen destination. We don't know exactly what lies at the bottom of that basin. We don't know if the Shapley supercluster is the last great attractor in our path, or if even larger structures sit beyond our cosmic horizon, silently steering our fate. What we do know is this: the more we map the universe, the more we discover that the stillness we feel is an illusion. Beneath the calm of the night sky, a vast, invisible flow is underway. Conclusion. Let's retrace our journey. We began with a simple, unsettling question. Why is our galaxy moving at hundreds of kilometers per second through the universe? We followed the trail from early galaxy surveys and the Seven Samurais' discovery of peculiar velocities to the naming of the Great Attractor. We saw how deeper surveys revealed a complex region of clusters and filaments, Hydra, Centaurus, Norma, and others, hidden behind the dust of our own galaxy. We learned that the Great Attractor alone doesn't explain all we see, leading us to even larger structures like the Shapley supercluster, and to the definition of our home supercluster, Laniakea, a gravitational basin containing tens of thousands of galaxies. We explored how all of this fits into a universe shaped by dark matter, dark energy, and the growth of structure. A universe where galaxies follow the contours of an invisible gravitational landscape. And we asked the ultimate questions. What does it mean to live inside a cosmic river? What does it mean that our galaxy's destiny is tied to structures we can barely see? How does it reshape our understanding of our place in the universe? The current scientific consensus is cautious and precise. The Great Attractor is not a single object, but a region of enhanced mass density in the direction of Centaurus, embedded within the Laniakea supercluster. Our local group's peculiar velocity of around 600 kilometers per second arises from a combination of influences: nearby structures like Virgo and the local void, the Great Attractor basin, and more distant concentrations, such as Shapley. Future surveys will refine our maps of these flows, and may reveal even larger patterns that connect our basin to others. But beyond the details, something larger lingers. The Great Attractor has shown us that the universe is not just a collection of static islands in an expanding sea. It is a dynamic, hierarchical, living structure of flows and forms. We are not at the center of the universe. We are not at rest. We are travelers in a galaxy swept along by currents carved in the fabric of space-time itself. We may never see the Great Attractor with our own eyes. We may never stand on some cosmic shore and point to the place that pulled us here. But we can know that it exists. We can map its influence. And we can marvel at the fact that, from a small planet circling an ordinary star, we've managed to glimpse the gravitational handwriting of the universe on scales beyond imagination. The universe is vast. The mysteries are endless. The journey continues.